Right, SEASTAR. Right, so I'm Christine Gommenginger, work at the National Oceanography Centre in the UK, Southampton, the UK. I'm talking about SEASTAR, a new mission concept for measuring high-resolution ocean surface current vectors and wind vectors. This is work we have done in partnership with Ifremer and various other people, Airbus and so on, which I'll talk about in a moment. So SEASTAR was submitted as a mission proposal to the ESA Earth Explorer 10 call, which, when was it? March, I think. Yes, March. Such a long time ago now. So it's led by myself and Bertrand from Ifremer, with Airbus providing the industrial support. This is the front page of the proposal that went in. It has a science team of 20 people, some of whom are in the room. But this was limited by ESA, who limited the number of partners to 20 people. But the full SEASTAR team is actually much larger than that, and we have spent a lot of effort to try and mobilize the scientific community across the world, and we have had an excellent response. We have something of the order of like 70 people, scientists, engineers, across 17 different countries who have expressed support for this mission. The decision was announced only a few weeks ago, so this is very new. In fact, I submitted this paper to this conference before I knew the outcome of the selection process. But the selection process was announced a few weeks ago, and so spoiler alert, if you don't want to know the outcome, look away now, as they say in football. Essentially, SEASTAR was not selected for EE10, even though we received excellent reviews. And I will give you a bit more gory details about this later at the end of the talk. So, this could be the end of the talk. So is it the end? The shortest talk of the conference? No. So I'm going to take this opportunity to remind people, and particularly ESA, about what they have just turned down, and see what we do about it next. So apologies for those who have already seen my talks about this before, because this is essentially an update on what the SEASTAR mission proposal was contained. So this is my understanding of what the ESA Earth Explorer philosophy actually is. I still believe that this is the philosophy for the ESA Earth Explorer, which is the route to to approve science-driven missions in the context of ESA. Now, clearly, that is perhaps no longer the case, but that is a discussion for later with a few beers, perhaps. So the idea there is that essentially the scientific community identifies a scientific need, and it drives the need for innovative technology which can answer that particular need. And the whole idea is that you need to demonstrate a certain level of scientific readiness and technology readiness as well. So that's the idea. Obviously, it didn't work. But this is how we framed the SEASTAR proposal, which I'm going to take you through briefly now. So the motivation for SEASTAR is this. So this is, Craig showed a sort of a variation of this figure earlier in his introduction. This is a picture from Sentinel 2 in the Baltic Sea, algae bloom showing this incredible structure at very small scales. You can see that the scale there, 10 kilometers. So a lot of these swells and fronts and so on, indicative of very strong vertical processes happening, divergence, convergence, and so on, happening in the ocean, happening at very, very small scales. And this is really the motivation for it. So we can see them in the hyperspectral images, high-resolution images, and SST. But we actually haven't got the dynamics, information of dynamics at those scales at the moment, because as was pointed out by Ernesto, you actually do need to know the vectors of the dynamics, not just one direction. So why do we need 1 kilometer resolution in the ocean, which is really what SEASTAR is aiming for? Well, we have identified from looking at the scientific community's requirements, particularly coming from the sub-mesoscale oceanography community, that really things change dramatically when you hit scales around 1 kilometer. Now, we hear a lot about sub-mesoscales, anything below 10 kilometers, but actually that doesn't cut it. Really, where dynamics change is when you go from when you reach 1 kilometer. This is what's shown here from a numerical model by Capet et al., running at different resolutions. And you see that the dynamics of this is sea surface temperature in the model, the dynamics change completely and become much more kind of realistic looking, if you like, once you hit the resolutions below 1 kilometer. And these are really important. I've already explained because of, this impacts the atmosphere-ocean coupling. That's not happening at 25 kilometers, I'm sorry, but it is happening at these very small scales as well. It impacts the upper ocean mixing, vertical transport, has a huge impact on biogeochemistry, because we see this in ocean color, because the marine ecosystem is responding to this. And particularly, the science identifies the role of geostrophic currents and surface winds, which of course is not something we can do using geostrophic current information from altimetry, for example. And of course, these small scale, you can say, oh, well, we don't really care about them, they're only in some places, but actually they are ubiquitous. And they've also shown to have to play a major role on global scales and climate scales as well. And there's a need for observation to improve the parameterizations in the model we use for forecasting, for example. The second aspect is the importance of these very small scales in the coastal and shelf seas. This is a picture again from Sentinel 3A this time. In the coastal zone, showing these sort of patterns of, in this case, sediment transport along the coast. And the models in coastal zones are now moving towards coupled systems running at very high resolution. 1 kilometer is really what they are asking for, right? So at the moment, they are not getting the data that we need. They need images at high resolution of dynamics, which they haven't got at present. The other thing, of course, is polar. I mean, this is another very challenging environment where we need high-resolution data for all sorts of reasons to do with the sea ice breakup, the role of waves and currents in sea ice, flow distribution, dynamics of how the ice actually grows and decays. And here again, we have got some really excellent results from the Sentinel-1 data, but again, it's not a vector type information, and there is room for improvement here. Okay, so SEASTAR science objective, just to hit the nail on the head, is to address this observational gap for ocean surface currents and winds vectors at the critical 1 kilometer scale, specifically in the coastal zone, in the shelf seas and polar seas. We have secondary and tertiary objectives also for improving the sea ice drift vector and directional wave spectra in coastal and polar seas, and some activity looking at river flow speed, for example, and inland water. But these are not mission drivers. Okay, so mission concept is based on the idea of squinted along-track interferometric SAR. So thank you, Roland, for the introduction to the interferometry, along-track interferometry idea. The idea of a squinted one is that essentially you do a long-track interferometry in two directions, looking forward and backwards. And I have a little illustration of that later on. We operate at Ku band. This is mainly because of heritage reasons and so on. There's no reason we couldn't do that at a different frequency. Ka band perhaps has also been considered in the past. What this does is it provides a unique new spaceborne capability to measure the total current, so not just the geostrophic, but all the ageostrophic currents, to measure the vectors in a single path, which also is not being done at present. The 1 kilometer resolution, I hope I've convinced you that this is really one of the drivers of this. So this is an absolute necessity for this mission. 2-dimensional maps. And then finally, these collocations of the currents, the wind, and the waves, which you do not have at present, and which is really characterizing the interface and controlling the coupling, for example, between the atmosphere and the ocean. And then finally, last but not last, this is a mission that actually is offering to do the systematic mapping of ocean currents and wind vectors at high resolution in coastal polar and shelf seas. This is not, sorry Paco, this is not something we're going to do occasionally, we're going to do it systematically, which is what this is, an ocean current mission. Right, technical concept, little graphics there about what we're proposing. So squinted ATR SAR, Ku band. As I just mentioned to Ernesto, our our analysis, and I think Adrien will be talking about this on tomorrow, is that we actually need 3 azimuth directions in order to be able to unravel the wind vector and the current vector, even when we include the Doppler information. The result of the many trade-offs between the science objectives and the technology to try and fit it into the EE10 envelope comes to this, ends up with this result of 170 kilometer swath, 30 degrees incidence mid-swath, etc., etc. 1 kilometer product resolution. There are a few fundamental things about SEASTAR which we cannot change. One of them is the interferometric baseline. Because of the decorrelation of the sea surface, we need to retain coherence between 2 looks of the sea surface. So that actually puts a limit on how far apart our antennas can be. And they don't want them too close, you don't want them too far. At the same time, we also need to achieve a sufficiently high SNR to achieve that coherence that we need. So there are demands for power, for example, but also the size. So the size of it is quite large. But we have worked very hard with Airbus particularly to try and fit within the EE10 constraints. So for example, one of the trade-offs is we have ditched some of the dual-sided kind of viewing ideas that we had from previous designs, such as the Ocean Surface Current mission concept that had been studied within ESA a few years ago. So we ditched that because it makes a much lighter structure, which actually satisfies the mass budget. We also have limited the operation to the coastal shelf seas and polar seas. So no longer do we attempt to do global coverage because we can't afford it, not within the context of an explorer. And this makes drastically reduces the power, the mass, the data budget, and of course the cost. Which is why we think that this actually does fit within EE10. Right, quick word on this because people will have seen this many times, but really just to illustrate the fact that we have reached an incredible high level of maturity with this concept. We have demonstrated the idea with an airborne demonstration campaign back in 2011 now, and this is something that Adrien published in 2016. We had this really very nice airborne campaign over the Irish Sea area in this star pattern, which I believe was Craig's idea to fly this. I don't know if you knew why you were doing this, but it's a really brilliant idea, and we should recommend this because it gives you the azimuth diversity, which has been absolutely essential. Yes. This was done in an area where we had HF radar measurements, DCP measurements, wave information, etc. And what this has done is that it actually helped us to understand some of these things about the wind wave effect in the Doppler measurements. And this is the result from that airborne experiment, from Adrien's work, based on the X-band airborne data from what was then called the wave mill system. And this is actually the similar kind of the surface velocity measured as a function of azimuth angle as shown by Alex Simouche for Envisat at C-band in the spaceborne concept. And the two are remarkably similar, which shows you that we have some great, we believe that we have some handle over how to deal with this. Incidentally, this effect is very large compared to the magnitude of currents. I mean, you can see the magnitude of this goes up to 1.5 meters per second. So these are really large, very large effects that cannot be ignored. And they affect all microwave Doppler measurements. And they vary in wind speed. I think Bertrand said that. Wind speed, direction, polarization, and incidence angles. So the different curves here, different incidence angles, and you see that the effect is strongest at near nadir. So again, something to bear in mind for other missions. Validation. Again, this is a highlight of this area, this sort of crossover area for the campaign, where you can compare the retrieved currents when you correct for the wind and wave effect. And you see this really wonderful agreement between the different overpass over this area. And then you do validations by comparing with HF radar. You see the little circles there are the results from the airborne data, and the big circles are the results from the HF radar. And where you can't actually see the little circles because the agreement is very good. Of course, these are vectors as well, so we retrieve the vectors information as well. And the performance is really excellent, where even despite this being an interferometric system on an airborne platform, we get errors that are of the order of 0.1 meters per second, which is extraordinary. Finally, just to show that we actually do have a retrieval framework in place, Adrien has been working on the geophysical inversion, working with Yves Kilfen here in Ifremer particularly, to come up with the way to do the inversion of the wind and the current simultaneously, bearing in mind the error levels in the instrument and so on. So we have worked very closely with Airbus to actually optimize the instrument specifications to make sure that we can reach the scientific objectives. And this is just a little highlight of the type of performance that we achieve for wind and current speed and direction as a function across the swath. I won't say very much about it because Adrien is talking about it in detail tomorrow. So I encourage you to come in and listen to his talk tomorrow. Right, the end? No. So where did it all go wrong? How come this wonderful mission was not selected? So here's a really short synopsis of the recommendations from the selection committee that says, ACO, that's the name of the selection committee, unique mission idea would be first along track, blah, blah, very nice, all very good, excellent. Secondly, mission idea judged to be very high quality and clarity, fulfills scientific evaluation, highly innovative, highly complementary to SKIM, hooray, as a medium resolution now, and the roadmap technology development is credible, hooray. Now, where does it go wrong? Well, nevertheless, probably needs a large customized platform which is expected to drive the cost of the SEASTAR mission idea, so that's where it goes wrong, right? So basically it's money. ACO recommends potentially pursue other avenues, because of the high likelihood of this exceeding target cost of E10. Of course, we are disputing this. We do not believe it exceeds the cost, and we will be querying that. In the meantime, it's not going to help because the decision is made. What next? We have shown that there is high scientific merit to this mission. We have widespread support across multiple disciplines, across multiple countries, and there's a high scientific and technological maturity. This is not the time to give up. And as one of my co-Is said, the only thing they could find wrong with it was the money. And that, which is a bit critical, but actually, when you think about it, it could be worse. Money can be found. SEASTAR remains the only mission able to address the observational needs of the ocean community for high-resolution current and wind vectors in the coastal, shelf seas and polar seas. It's complementary to SWOT, SKIM and Doppler scat. WaCM. I haven't got time to go into this, but there's very clear complementarities there with these other missions. And we are now looking for other avenues, in the words of the selection committee, to take this concept towards implementation, including outside ESA. Summary, it's a very highly innovative mission concept that was proposed to deliver new imaging capability, high accuracy imaging capabilities for ocean surface currents and wind vectors at 1 kilometer resolution. Complementary with what I've said, that high level of scientific and technological maturity, but it was not selected, and we're looking for other avenues. If anybody has got $500 million, 500 million to spare, come and talk to me. Thank you. No time for questions, I guess.
Yeah, you do have questions. Always. With me, I have no watch.
You have no watch.
I'm only a Luke Van Mark to wait for me.
Oh, well, that's okay then.
So, is this on?
Yes.
First of all, let me say how sorry I am. It would be really, really beautiful to get images like what you can get from Doppler scat from space. I think one of the major things that I have found that making the case for a mission like this is the poor temporal coverage and just localized regional models. So do you have any ideas as to how to do that?
So the Explorer opportunities, if you like, are not really concerned so much about what we call monitoring, or operational aspects of temporal coverage and so on. So we are not too worried about achieving global coverage or frequent temporal sampling from an operational point of view. What we're really looking at is getting data to improve the science, to do the research of how these processes evolve spatially and temporally. So actually the orbit that we have chosen has got a fast repeat phase, very much like SWOT is doing the one-day repeat. And we actually proposed to extend that particular phase to operate it in several times, several periods during the mission, to have a one-day repeat, to look at the temporal decorrelation of those features. Because really it's about the science. It's providing the data to improve, to get the observations to improve the parameterizations of those processes by understanding their spatial structure, their location, variability geographically and seasonally as well, because we know that they change in those, and also temporally in terms of of the order of a few days.
To just help, it's just like I think it's not a question. No wonder you will never match at this scale the capability to revisit. So most important is to catch not 5F, not 10F, but believe me, 40 times F. And this is sometimes what is completely missing from model. And this could be caught by this type of measurement. So even one would be good. And remind that there is no capability in time to catch with this event. They are transitory. And so it's not what we have to aim. We have to aim to be very precise in terms of quality and spatial description. Okay.